All right, so now we're going to talk about what is called the Levi-Civita or Riemannian connection. So, for most of this course, it's like we've been talking about sort of these two ways of thinking about straight lines. It's like, right, one of which is in terms of affine connections, or sorry, generalizations of straight lines, if you will. One of which is in terms of affine connections, right, and the idea that the direction stays the same, right, and the other in terms of this idea of length minimizing curves, right. So, and we've been treating again affine connections separate from the Riemannian metric, which is then used to, it's like make sense of the notion of how long a curve is. Okay, so all this comes together, it's like through what is called the Levi-Civita connection. So operationally, one way of thinking about this is that this is a distinguished affine connection which we can associate with a Riemannian sort of structure. It's like on a manifold, okay? And it has a few nice properties, so let me sort of try to talk about it. So one of which is that so there's this idea that this connection, well, there's this idea of metric compatibility between a connection and a metric structure. So there's this idea of metric compatibility, right? So what that basically means is that if you, so that shows up in two ways, right? So one of which is that the magnitude of a vector does not change under parallel transport. Right, so if you have a vector A, you can make sense of its length, if you will, or this length squared, right, by taking the inner product of that vector with itself with respect to this Riemannian metric, right? So if you start off with a point cos C0, and then you look at what happens when you parallel transport this vector and end up at cos C1, right? So so if you take this vector and you parallel transport it from cos C0 to cos C1, and that inner product stays constant, then there's a sense in which the vector, the magnitude of the vector doesn't change under parallel transport, right? So the second thing is when the inner product of two vectors doesn't change. So the inner product of two vectors do not change under parallel transport. And of course, it's like if you have this condition, then the first condition obviously holds, right? So as you might expect, it just means that you now take the inner product of two different vectors and you parallel transport those two vectors. And that inner product between them doesn't change. Okay? So, so let's look at what that condition looks like. And what it means. So if you take Gij, it's like at cos C plus d cos C. So I'm going to essentially move that point infinitesimally, right? So this is equal to EI cos C plus d cos C, EJ cos C plus d cos C. So this is just the definition of the components of the metric tensor in terms of the inner product that's like between basis vectors, right? Right. Okay. So you can write this, it's like in terms of the connection coefficients. Well, let me just sort of write them as a perturbation, right? The EI, EJ C plus D EJ at this point. So I can write Gij at C plus D C as Gij at C plus, so I'm essentially just doing a Taylor expansion here, right? So the partial respect to K of Gij D C K. All right, so this is just the linear term, right, in the Taylor expansion. Okay, so that's telling me that this thing, this term here, right, to leading order is like the DEI paired with EJ, right? So let me just write it this way. So this is telling me that, you know, D K G I J D C K is going to be equal to this piece interproducted with that, right? So this is D E I E J plus E I interproduct D E J. Right, and if you recall, it's like these things, right, are giving you the connection coefficients. Okay. Right. So this is going to be gamma Kij plus gamma Kji. Okay, anyhow. Right. So this is telling you something about this idea of metric compatibility. So this gives you a coordinate characterization of metric compatibility. Right, and then so it turns out that metric compatibility in and of itself is not enough to uniquely specify a affine connection, but if you have metric compatibility together with symmetry, so so symmetry is basically saying that there's some equality, it's like of the metric coefficients under interchange of some of the indices, right? So if you interchange the first two indices, right, and the metric coefficients stay the same, it's like then we say that that affine connection is symmetric. So it turns out that if you have a affine connection which is metric compatible with a given metric tensor, and it is symmetric, then there is a unique affine connection which satisfies that. So, so the theorem is that so there is a unique sort of metric compatible symmetric affine connection, which we refer to as the Levi-Civita connection. Or Riemannian connection. Okay, when it's given in the following way, you can write down the connection coefficients, and it's just 1/2 involves derivatives on the metric. Okay, and I should remark that sometimes instead of pairing metric compatibility with symmetry, you can also pair metric compatibility plus what is called torsion freeness. Also gives you the Levi-Civita connection. All right, so let me sort of not go too much into the details about this notion of torsion, but let me just sort of say intuitively that curvature, which we've discussed before, measures the sense in which the tangent spaces roll as you go around in a loop, and then torsion measures the extent to which the tangent spaces twist as you go around a loop, right? And so in any case, you can obtain a unique affine connection. It's like on a Riemannian manifold by requiring that that affine connection is metric compatible and symmetric, or by requiring that it's metric compatible and torsion free. Okay, and both of them lead to this Levi-Civita connection, which we're talking about. Okay, so the another important part of the property of the Levi-Civita connection is this thing we had been discussing before, which is sort of this two notions of generalizing. What it means is like to have a line which is straight on a manifold, right? And we've already seen it's like how we can make sense of geodesics, for example, using an affine connection. And the theorem basically is that if you use that notion of geodesics with respect to the Levi-Civita connection, that is equivalent to the notion of length minimizing curves, where you measure the length of the curve using the corresponding Riemannian metric. Okay, so the theorem is as follows, right? So a curve that connects two points by a minimum distance is a geodesic under the Levi-Civita connection. Where the length of the curve C is cos C of t, right, connecting cos C0 and cos C1, right, is given by the following. So as you might expect, it just involves differentiating that curve. It's like thinking of it as a tangent vector and then measuring the length of that tangent vector. It's like and integrating it over the curve. So this length is the integral from 0 to 1 of the square root of the inner product between cos C dot with itself, right? So this is given by Gij of t cos C dot I of t cos C dot of j of t dt. And we have to take the square root because it's like when you take the inner product of its length, you get its squared length, right? So in order to get the length, you need to do that. All right. So I should say that if you read it's like the statement of the theorem, you'll see that it only goes in one direction, right? So it says that a curve, it's like which connects 2 points, it's like by a minimum distance with respect to this notion of distance using the Riemannian metric, is a geodesic in the sense of the Levi-Civita connection, which is to say that the curve doesn't change direction, or that its covariant derivative, it's like of the tangent vector along the tangent vector is 0. Okay, and that's because there's another possibility it's like which can happen, which is that you could have, say, a maximizing a length maximizing curve, right, which would still satisfy the geodesic equations. So so it's not necessarily that a geodesic is going to be minimum distance. It's going to be essentially stationary in its distance, basically, right? So that's sort of the reason why the implications don't go both ways, because if you sort of view this variationally, all it sort of says is that that length, it's like something which satisfies the geodesic equation is going to be such that the length of that curve is going to be stationary with respect to small perturbations of the curve, right? So that doesn't necessarily imply it's a minimum. It could be a maximum. It could be a saddle. So that's the reason why the theorem is only stated, it's like in one direction. Okay, so let me just stop here.